Hello? Okay, wait a second. So does this work? The slides do not change with this? Do they? Okay, no problem. That's fine. That's fine. Okay. So today I'm going to talk on coding theory. How many of you heard of coding theory before? In any form before? Okay, very less. Okay, fine. So this is going to be an overview talk of coding theory, like what happened in, let's say, past 50 years, what have been the advances in this field, okay? And if you find it interesting, maybe you can go back and read some of this stuff. So first we'll start with the most basic things in coding theory. Why do you think is coding theory important? I mean, anyone? Any guesses? Okay, fine. Let me just explain. So, I mean, coding theory comes in the context of channels. Like, there is a channel somewhere, okay? Between a sender and a receiver, there is a channel. And typically, the channel is noisy. So, something is transmitted and something else is received. That's how it is all the time. And that is because of the channel noise. And that is what the nature gives us, which is not under our control. Okay? So with this noisy channel, you want to send the message across. And the way to do it is to add some redundancy. Okay? So instead of sending just the information, okay, add some redundancy to it and send it and hope that it will get across. Okay? So that is the basic motivation behind coding theory. You add your redundancy in a controlled way to the transmitted message. There's a message to be transmitted and you add your redundancy to it and hope that it will be recovered reliably at the receiver. So this is a motivation. Okay. So this is one of the channel models. So in this talk we'll see some channel models, and all of these channel models have come up in different contexts. They have, I mean, practical significance and all that. I'm not going to motivate the practical significance of this channel model. This is the simplest channel model which comes about in coding theory. Okay? So this is a binary symmetric channel. So there's a sender who wants to talk something to the receiver, and the sender talks in terms of bits. So the input is either a 0 or a 1. And the receiver receives the bits, but what channel is in between the wire is noisy. So 0 can go to 0 with a probability 1 minus p. 0 can become a 1 with a probability p. And it is symmetric, so 1 can become a 0 with probability p and 1 remains a 1 with probability 1 minus p. And this p is termed crossover probability. So let's say it is 0.1. Okay. So now, what is the probability of error? Like, when you receive some message, what is the error probability? Now, if you don't do like coding what I have told before, I mean, then the probability of error of 0.1 can be, I mean, you keep sending your zeros and ones, don't do anything to it, and the probability of error at the receiver will be 0.1, because all that the channel is doing is flipping with the probability of 0.1. Okay? So, but let's say that I want to reduce it to 0.03. So which is less than the crossover probability of the channel, right? So what do you think should we do? Okay, redundancy in what way? Simple way. Parallel system means here we are sending bits. Here we are just sending zeros and ones. So we have to do something to zeros and ones. Okay, checksum. But the most simplest way that you can think of is repeat, right? You are sending a 0. Instead of a 0, send 0, 0. You are sending a 1, instead of that send 1 1 and hope that, I mean, if you calculate, probability will be lesser than if you just send a 0 or a 1, right? Okay. So the simple scheme is to use a repetition, and why I have written 3 is that, I mean, there's a clear majority. You can see that if 0 is repeated 3 times and it is sent, and or 1 is repeated 3 times and sent, okay? If any one bit you got it 2 times, okay, you will say that is the bit which has been transmitted, okay? So this is the decoding scheme. The decoding scheme is just a majority rule. This basically applies for odd lengths, but that is just a technicality. So what is the probability of error in this case? So if these patterns are observed at the receiver, which is 0, 0, 0, 0, 0, 1, so there are 2 zeros in each one of these sequences. So all these, they are decoded correctly if a 0 is transmitted, right? And suppose the message was 1, I mean the message is 0, but you receive one of these things, then you will decode it in error, right? And the probability you can calculate that this is 0.028. I guess this probability is easy to calculate. So P is, I mean, you just, there are independent 3 times you are sending it independently, and you want to check with what probability I will get this. If I send a 0, 0, 0, with what probability I get this, with what probability I get this, and so on, and I just add them. So that is a simple calculation. So now suppose if I want to decrease the error probability even further, okay? So I want basically the error probability to be in my control. So I want a required error probability, and let's say I want to decrease it further. Then use the same trick, but repeat this some n number of times. Okay, instead of once, I mean instead of thrice, repeat it n times. And in this case, the rate is 1 over n. Use the same decoding scheme, and you can calculate the probability of error for this setting as an exercise. You can just try it out. Now, what's the drawback of this scheme? Any clear? Yeah. Yeah, so what is the time problem? So suppose if I want my probability of error to be quite less, then how much time should I keep sending that 0? I should keep sending that 0 enough number of times so that that 0 just goes across, and similarly 1, right? So this is a table which shows how does the probability of error and the length of the code, I'm sorry about this, length of the code, I mean length of this repetition compare. So you want probability of error 10 power minus 4, you use repeat 13 times, 10 power minus 7, repeat 25 times, 10 power minus 10, repeat 39 times, and as you keep increasing this number keeps increasing. So if you want the required error probability, rate of transmission decreases, that's there, but this rate of transmission, if you want this to be as low as possible, this almost goes to 0. You should keep on transmitting all the time. Okay. So in that sense, this is a name and a bad scheme. With respect, in coding theory parlance, it's not a good code. Okay. So now, how do you improve this rate? So what was it that we were doing, I mean, not doing smart in the previous scheme? Receiver is receiving either some version of 0 or 1. That's there. Yeah, that is there, but let's say there are no acknowledgements possible. I mean, let's say I disallow acknowledgements. So this is what is called, like what he said, I mean, if there are acknowledgements, it's a different paradigm. But this, whatever coding I am going to talk about, is called forward error correction. So the transmitter just transmits and doesn't ask for an acknowledgement from the receiver. Okay? And still we want the probability of error to go down to 0. So what we were doing wrong was that we are adding redundancy every bit. We are saying, okay, I receive a 0, I am adding redundancy to it. I receive a 1, I am adding redundancy to it. And we are doing it every time. Okay? So a smarter way to do that is that collect a block of bits, okay, some of them, and add a redundancy collectively to that. Okay, that is what is checksums or whatever. Okay, so that is what is done here. So there are some blocks here, and these blocks together there is a redundancy added to get a larger number of bits. So the first code which has come up in coding theory, I mean the code which has like invented the field of coding theory, okay, by this block based scheme, is what is called Hamming code. So Hamming, he was working in Bell Telephone Laboratories, and he was very much annoyed by one problem that they were facing. So there was an error prone punch card reader, okay. They could detect errors, but somebody has to go and manually correct it every time, okay. So he was very much annoyed with this problem, and he said, okay, can't I design a code which can correct errors? Let's say I just want to correct one single error. Can I design such a scheme? Okay. So the simplest version is called the Hamming code. Whatever Hamming code he has come up with can correct a single bit error, and it can also detect single or 2-bit errors. So this is what the code can do. This is the capability of the code. So now the code that he has come up with is shown pictorially here. Okay. So there are these 3 circles, and M1, M2, M3, M4 are the messages. Okay. P5, P6, P7 are checksums or parities, you can call. And P5 is whatever the sum of the messages which appear in this circle, this M1, M3, M4. And this arithmetic is called mod 2 arithmetic. You are aware of mod 2 arithmetic? Yes? So 0, 0, 1 plus 1 is a 0, right? And rest everything, there is addition, and 1 plus 1 is a 0. That is mod 2 arithmetic. Okay. So here P6 is the sum of M2, M3, M4, and P7 is the sum of M1, M2 and M4. Okay. So suppose if the messages were of this form, okay, so which is 1, 0, 0, 1. So that is the messages, and you have to generate parity for this. So P5 is 1 plus 1, 0. P6 is 1 plus 0, 1, and P7 is 1 plus 1, 0. So this is a code word. So message has been mapped to a code word. Okay? A 4-length message has been mapped to a 7-length code word. So now, in general, what is a linear block code? You take k message bits, okay, and map it to a code word of length n. So these are the parameters of this block code, okay? And each set of k message bits has to be mapped to a unique code word. I mean, for each message there should be a different code word. That is the first thing. And second is that I am calling it linear. So each of the n bits is a linear combination of this k message bits. Okay? So that's why this word linear here. So n is called the length of the code, and k, the k message bits that we used, is called the dimension of the code. So these are the parameters of the code that I am introducing slowly. Okay. So there is another, I mean, how do you generate the code? There is a way to generate it, and because it's a linear code, it can be generated using what is called a generator matrix. So code is the message multiplied by a matrix, which is called the generator matrix. So the generator matrix, this what I have shown is for the Hamming code that I have shown earlier. Okay. So this is what? This is M is 4, G is 4 cross 7. Okay. The first 4 columns are identity, which means by multiplying it with M, you get just the 4 message bits. So the first 4 columns give you the 4 message bits, and the last 3 columns give you the 3 parity bits that you saw. Okay. And you can verify. The first parity bit was 1, 3, 4, second was 2, 3, 4, and third was 1, 2, 4. That was what was given in the diagram. Okay. So this is what is called the generator matrix of a code. So now there is a dual viewpoint of a code, which is called the Parity-Check matrix. Okay. So this is another way of defining a code. And what does this matrix, how do you define this matrix? It is a matrix which, when multiplied by, you multiply by any code word here, will result in a 0. Okay. So all your code words are in the null space of this matrix. Right? Have you heard of null space before? Okay. So all the code words are in the null space of this matrix. And how can you come up with this matrix for the Hamming code? Okay. So earlier I wrote P5 equals M1 plus M3 plus M4 mod 2. But in mod 2, let's say I want to take all those message bits to the left hand side. Okay. But a minus can be, -1 is nothing but a +1 in mod 2 arithmetic, right? So because 1 plus 1 is 0, so -1 is nothing but +1. So you can replace all minus with plus, okay? And the equations that code words satisfy are P5 plus M1 plus M3 plus M4 equals 0, P6 plus M2 plus M3 plus M4 equals 0, and so on. So these three equations, okay? From these three equations, we want to find out this matrix H. So how do you do that? So we have this 3 cross 7 matrix, and C is first 4 are M1, M2, M3, M4, and the last 3 are P5, P6, P7. So based on that, this equation can be represented by this row, okay, which is M1 plus M3 plus M4 plus P5. And similarly, M2 plus M3 plus M4 plus P6 equals 0, and so on. So that is, so this is a parity check matrix of this code. This point, just this matrix, okay. So this is, so the C that we have, the column vector is M1, M2, M3, M4 and P5, P6, P7, okay, in that order, okay. So let's say I have all those things lined up with this column C, okay, and I want to represent this equation as HC transpose equals 0. So I want to come up with this first row. So where will you place these ones? So 1 will get multiplied with M1. If you see the way matrix multiplication happens, right? So this times, so I can just write it down on the board for you. So this is your, okay, M1, M2, M3, P5, P6, P7. Why I am writing this is what will be multiplying the corresponding vector. So this is M1, M2, M3, M4, P5, P6, P7. We want this to be equal to 0. So you want the first vector here as the first equation there. So you have to place the ones. So M1 there's the 1, M3 there's the 1, M4 there's the 1, P5 there's the 1. Okay? And so on. The next equation is represented by the next row. And the third equation by the third row. So that is how you come up with this parity check matrix. Okay. Yes, C transpose was a vector. C transpose is a column vector of the corresponding to the code word. So if you use the generator matrix that I have shown before, and as you keep varying this M1, M2, M3, M4, how many combinations do you get? Each takes value 0 and 1. So you get a total of 16. So there should be 16 code words in our code. And I have just listed all the 16 code words, where the first are this M1 through M4, and these are P5, P6, P7. And these are the code words. And we want to understand there is a terminology which is called minimum distance of a linear block code. So what is minimum distance? If you forget this entry 0, okay, it is the minimum weight of any code word, okay, or to define it itself, you take the distance between these two vectors. What is the distance between these two vectors according to some definition that you define, let's say the second and the third vector? What is the distance between these two? 3. So this and this. So they are agreeing in all the other positions. They are disagreeing in 3 positions. Okay. So this distance is called Hamming distance. And the codes are generally designed for a good Hamming distance. So in this whole thing, we can verify that any 2 code words you take are separated by a distance at least 3. So that is the minimum distance of Hamming code. Hamming code minimum distance is 3. So, and it is not in general true that, I mean, any minimum weight code word is the minimum distance. Only for linear codes, okay. in linear codes what happens is that whatever picture you have with respect to 0, that's the picture with respect to any other code word. It's just like a translation, what is happening. When you are standing at some point and looking at everything, it's like you go to some other point, it just looks like a translate. So in that sense, to find the minimum distance, you need not have to take every two vectors and see, okay, what is the minimum distance. You can just see the weight of the code words and see which is the minimum weight code word. So this technique will work only for linear codes. So what will we do with this minimum distance? What is the significance of this minimum distance? As we said earlier, there is a code which has some error detection and error correction capabilities. Okay, and using minimum distance, you can define both. What is the error detection capability? So what is meant by error detection capability? I look at the code word, I know it's not correct. Okay, so that is called error detection. Okay, then I have detected an error. Okay, what is meant by error correction capability? Okay, so it should be able to correct those errors also. Maybe you can say there is an error, but you don't know which is the correct code word. Okay, so it has both error detection and error correction capabilities, and you can use it is like, you know, modes of your maybe phone or something. You can use in one of these modes. You can either use it in error detection mode or use it in error correction mode. So what is the error detection? How many errors? Suppose if the minimum distance is d-min, okay, how many errors can be detected? Because any two code words, you know, are separated by d-min minus d-min, right? So suppose if I have a code word like this, C1, and I draw a ball of radius d-min minus 1 around this. Okay, so what is this space first of all? This space is f2 power 7, which is 0, 1 power 7, which means I take all 7 length vectors of constituting 0 and 1. That is this total space. In this I am marking my code words. I have marked only a few of them. Actually there are 16. I am showing only a few here. Okay. So now around this point C1 I am drawing a ball of radius 2. 3 is the minimum distance of the Hamming code. Okay. I am drawing a ball of distance 2, which means that anything which is a Hamming distance 2 or less will fall within this ball, right? Actually it will not be a ball. Okay, this is not Euclidean distance, you can't imagine it like a ball, but for the sake of convenience I just used a ball. Okay. So now if I draw a ball of radius 2, so everything that falls below this, I know it's not a code word, definitely, right? So then anything which comes here, I know I can detect errors in that, right? So if I transmit a code word and I get any vector within the radius of 2, I can certainly detect errors. So the error detection radius is d-min minus 1. So because d-min, when you draw, you will hit C3 also, and C3 is a code word, right? So you know that C3, then it could be that C1 is transmitted or C3 is transmitted, you don't know, you have no way to detect errors. But if it is within a ball of radius 2, then you definitely know if it's an error or not. So then what is the error correcting radius? The error correcting radius is half this, because there will be a ball around C1 and there will be a ball around C3 also. Okay. So now if there is a code word here, somewhere here, okay, so I don't know whether, this is, when I said error correcting radius, this many errors I can correct for sure. If I am using my code for error correction, this many errors I am definitely correct. I can definitely correct. Okay. So this is half the distance. d-min minus 1 by 2, but will it be a floor or a seal? It should be a floor, because we should be always on the safer side when we are claiming something. When we say, okay, I will definitely do this, we should be on the safer side and we should take a floor. Okay. So this is the error correcting radius, and that if you used to plug in 3, it is 1, and that's a Hamming code can correct one error, one blade flip always.
What if it is more than the Hamming distance in this case? What if it is more than 3? The distance, whatever we saw in the other example.
Correct.
Can it be more than 3 in any case?
Distance can be 3, more than 3. So there, So there are, I mean, some code words are separated by 3, but some other code words can be separated by 4 also.
For this example, if it is, let's say it is for now 6 or something.
Yeah.
Because there are 7 bits.
Correct.
Then how can I assure that I can detect 2 bits, either in 2 bits?
But because the distance between any two code words, so this, around this if I draw a ball, okay, within a distance of 2, I mean within a radius of 2, there is no other code word. 6 is coming, 6 is the distance between those two code words, but that is also greater than 3. Right? So here we are giving the worst case guarantees. So that is the error detection and correction. Now, I mean, like we saw in the case of repetition, I mean, coming up with a scheme is important, and how to decode this code is also important. Means you are given code words and noisy versions of those code words, and you should be able to decode. That is the challenge. So what is the decoding employed is called maximum likelihood decoding. That is the technical term. Okay. And whatever majority rule we saw earlier for repetition is an instance of this for that code. Maximum likelihood decoding. Okay. So what does it mean? It is again common sense. Okay. So y is the received vector. It's of length 7. Okay. And which is the code word which we want to decode it to? Okay. We want to decode it to that code word which maximizes this quantity which is called the likelihood. Okay. That we want to decode it to that code word from which y could have been most likely occurred. Okay. So because there are so many x's, from any one of those y could have occurred, right? But we want to decode it to that code word from which y would have most likely occurred, right? So that is what is maximum likelihood decoding. So this is, it maximizes this quantity. And this maximum likelihood, let's say for our example, binary symmetric channel, okay, what could it be? Because each one of those 7 things are independent instances, right? So if you want to translate, maximum likelihood is a general principle. If you want to apply it to binary symmetric channel, okay, then it is nothing but a simple nearest neighbor decoding. You place your y in the space, okay, and decode it to the code word which is nearest of all, I mean, to which y is nearest to. And this can be shown as equivalent to the maximum likelihood decoding. So this is a nearest neighbor decoding, and there are several schemes like efficient algorithms to do it and all that. But basically this is the principle. Yeah, right. That's true. Actually, probably very greater than half is like a degenerate case. Maybe we just don't want to send. No, it's not even that. You just randomly toss a coin at the receiver end, and whatever you get, you say that is what it is, and you be happy with it, and you will get a better performance anyway. Right? Okay. So whatever we saw till now was linear block codes. Okay, we took a set of k bits and we encoded it to a set of n bits. But generally what happens is that in practice, I mean, this could be done, but then there is another school of thought where there is an input stream, bits are coming, okay, and you don't want to break it off into the scale and blocks. Okay, the stream is coming and you want to generate an output stream. And so as and when the input is coming, almost you want to keep generating your output. You don't want to wait for K to come and then encode it. So that is where these convolution codes come. So these are another class of codes where the encoder has memory. Okay. So what happens is that, see, basically how much memory the encoders have is that many bits that you are storing as the stream is coming, right? If your encoder has some memory, you are storing so many bits and discarding the rest, because rest everything is passed and only these many bits are required for my encoding. So that is what I have shown here. There is an input sequence UK, okay, and I am going to generate 2 parity sequences, okay, which means at any instant I am getting 2 parity bits, but in general I have 2 parity sequences. Okay. So and then what is happening is that this sequence UK, I am passing it through two shift registers, which means I am delaying. Okay. So I have UK, but then I have here access to U of k minus 1 and U of k minus 2 also. So here my window of encoding, the memory is 2. So because I am remembering the past 2 bits also in order to generate the current parity bit. Okay. So now then how am I generating the parity sequence? That is UK plus UK minus 1 plus UK minus 2 is one parity sequence as this sequence keeps coming. And second is UK plus UK minus 2. So these are the two parities I have generated. Okay. So this is a simple way to look at the encoder itself, because I mean it's just using shift registers and I can forget everything in the past. It just has a memory of 3. Okay. And this has a very nice encoding also, decoding also possible, which is called Viterbi decoder. Okay. I am not going into the details of that for this talk. Okay. For those who are interested, it's a very nice algorithm to know, Viterbi algorithm. Okay. So that is what is used in decoding the convolution codes, and which makes this highly practical and can be implemented and all that. So till now we have seen block codes and convolution codes. Okay. So now, just to get a glimpse of some more channels, okay, first I have shown binary symmetric channel. Okay. I will show 2 more channels which are generally employed in different settings. Okay. Binary symmetric channel might be employed in one setting, erasure channel in, so let's say some storage setting, and so on. Okay. So but good to know some channel models, because the channel model critically determines what code you will be using. So now, so this is called the erasure channel. So what is meant by an erasure channel? So erasure means there are no errors, first of all. In the erasure channel there are no errors. This is a binary erasure channel. So which means input is a 0 and a 1, but output, if it is a 0, I mean it can be a 0 or it is erased. Okay. But it can never be a 1, because there are no errors in this channel. So but there are only erasures, and this erasure is represented by this question mark. So 0 can become a question mark, 1 can become a question mark, but otherwise 0 remains a 0 and 1 remains a 1. This is called a binary erasure channel. This is used in some storage systems. I mean not binary, in general erasure channel is used in storage. Now second most important channel is what is called additive white Gaussian noise channel. Yeah. Question mark represents that, see, I know that a packet is erased. Packets are coming to me. I know some number packet has not come to me, but I know that it has not come to me. If it comes, I know it has come correctly. Otherwise, I know that it has been erased somewhere, right? That's what the question mark represents. So this is additive white Gaussian noise channel. So in the previous 2 channels, the input was discrete, the output was discrete. Here in this channel, input is continuous, output is continuous, which means it takes values from real numbers. Okay. So output has some input plus a Gaussian noise. Okay. And all of you know Gaussian distribution. Yes? Okay. So this is a Gaussian distribution, and typically in these things the mean of the Gaussian will be 0, which means the noise is just adding some fluctuations around some 0 value. Okay, that's what generally the noise does. Okay, and typically this white Gaussian noise in a communication system, it will get added at the receiver, the electronics, at the receiver electronics, right? Some noise is generated, and that is typically modeled as AWGN channel. Okay. With some, so there is this variance sigma square, and this sigma square is what is characterized with that receiver electronics. How good, and if you make it, so suppose the way it works is that, suppose if you put this receiver electronics in very less temperatures, so this noise is proportional to temperature, okay, receiver noise. So if you put it in very less temperatures, so you can be assured sigma square is very less, and so on. Okay. Now, so given the channels, so we have studied the some preliminary examples of codes and channels. So now we will see what is the fundamental limit which means the bound which the channel itself places on you. So because the channel is noisy, you can't transmit above a certain rate. Okay? So you can't keep pumping in infinite number of bits into a channel. No, that is not possible. There is some limit to what you can transmit over the channel. Okay? And that limit is what is called channel capacity. This is by the greatest work which has ever came about in information theory, which started this information theory and coding theory fields, by Shannon in 1948. His paper is called A Mathematical Theory of Communication. And this coding theorem is also a part of, or maybe a revised version of his paper. So in that, so the channel coding theorem, so this is for any channel. You take your favorite channel, apply this theorem and find out its capacity. That's how it is. Okay? So now there is an input X and an output Y. Okay? And both are related by a conditional distribution like this, which means I give you an X and Y can occur with some probability, and that is what is represented by this conditional distribution Py given X. Then, so if such a channel is given to you, the channel capacity is max over all possible source distributions, because X, the probability distribution of X is nothing but the source distribution. X is your input, okay, of Ixy. Okay, this Ixy is what is called the mutual information between the random variables X and Y. So it actually represents how much information the Y has about X in a probabilistic sense. Okay. So in order to understand what this Ixy is, okay, so now I told you before that we are free to pick the source distribution. Now this Ixy is nothing but what is h of x minus h of x given y. So h of x is a measure of uncertainty in x. Okay. Already the source has some uncertainty. Okay. So if I say 0, 1 tossing with some probability p 1 minus p, it already has some uncertainty in it, some amount of uncertainty. Okay. And this h of x given y is the uncertainty in x after you know y. Okay. And what this mutual information is how much this uncertainty has reduced, that much information you have got about x. Okay. And that is what this mutual information actually signifies. And that is what will be, was used in channel capacity. Okay.
So if x and y are independent, does it mean capacity is equal to 0?
Yes, of course. Because your x is giving you no information about y. Y is not giving you no information about x. So then the capacity is 0.
I don't understand channel capacity.
See, because whatever you are transmitting, you assume that whatever you are receiving is some function of that, means related to that in some way. And independence actually means there is no relation. So which means the channel capacity is 0, right? If the channel capacity, if the channel were like that, you are talking about a channel where I am talking here something else, but somebody is receiving to somebody else, maybe. Okay, then there will be no correlation between what I am talking and that guy is listening. So the channel is independent, right? So this h of x is the most important term which has been defined in information theory. Okay, and the beauty of this is that it defines a measure of information. Okay, nobody before that has ever tried to measure information. Okay, in terms of this random variable, so nobody has tried to measure information. So once you have come up with a measure of information, everything else starts making sense. Okay, but the way this function itself, this I have shown where x is binary. But the way this function itself has come about is like you start defining your axioms that your measure of information should satisfy. Okay, so you start saying, okay, this has to be my measure of information, so it has to satisfy axiom 1, axiom 2, axiom 3. This is how I want my measure of information to be like. Okay, so if you start putting down those things and see which functions actually satisfy these axioms, it turns out this is the only function which satisfies those axioms. Okay. So which is, let's say P0 is the probability of symbol 0 and P1 is the probability of symbol 1. Okay. So minus P0 log P0 minus P1 log P1. Okay. Let's say it's taking m values. So 0 to, let's say 1 to m. Then what will this function be? Up to m. So it's only P1 log P1, P2 log P2, Pm log Pm. And this function satisfies what kind of axioms you would have liked information to have, which is some addition axiom, simple axioms. Not too hard, but I am not going to go through them, but simple axioms. So this is the intuition behind channel capacity. So what people have been trying after Shannon has actually come up with this channel capacity is to come up with codes which actually reach this channel capacity. Okay. Many codes which people have constructed using nice techniques in mathematics, they were not going up to channel capacity. Okay. And they were always trying this. And but Shannon himself has told one thing. Okay. He has come up with this expression for channel capacity, and he said that there are good linear codes. Okay. Good linear codes. What does he mean by good linear codes? One is that rate of the code has to be close to the capacity. That is one thing. Second, when you use that code, probability of error has to go to 0, because capacity means only that. You are taking actually only those codes or families of codes for which the probability of error actually goes to 0. That's what we have said, that repetition is not bad code, because for that rate goes to 0 as your probability of error goes to 0. But the channel capacity would have been some positive value, right? So he said there are good linear codes, but he left this coding theorist to find out what these good linear codes are. He just said there exists. Okay, there's a big space, and in that space they do exist. Okay, so this was great news. But then these codes, whatever he were telling were good, also require a very large length. Okay, they require a length, but the rate will be positive. Okay, but they still require a large length. So this is the catch. So to design any good codes, it turns out that we have to employ large length codes. So we will see some codes for used in communication systems. So there is a reason why large length codes are required. Okay, and that we'll just see why. Okay. So the reason is, suppose if I take a code of length n. Okay, what did our binary symmetric channel say? 0.1 probability I will get an error. The bit will be flipped, right? So on an average 0.1 n bits are in error, on an average. Okay. So but then when is this close to reality? Okay, this is called what is called law of large numbers and all that in probability, right? So this is close to reality only when n is large, right? So the deviation from this 0.1 is very less only if the n is large. So if you want to design a code in order to be able to correct so many errors, okay, so your code will be performing well without errors only if your n is large. In first place you design such a code, right? But if you design your code for a smaller length, what happens is that, I mean, this is an average number, that's fine, but this deviation comes into picture, okay, and you will start seeing more errors, and then that increases the probability of error. Okay, so that is why it's always, I mean, it's a advice in coding theory to design codes of large n. I mean, large n depends on the application, and I mean, it's like maybe 1000, maybe 10,000, in that range. Okay. Now, with the large length itself comes with some practical aspects. As the length of the code grows larger, we saw in convolution code it was okay. So the block code, you want a code of length n, and you want the rate of the code to be high, so the k is high, so which means my encoding complexity is high and the decoding complexity is high, right? I mean, as the block length grows larger, they scale. So if you are using them in your device, you just keep waiting and just for a very good, because you have employed a good code, you are just waiting, and this is not what you want to do. Okay, so this is another breakthrough which happened in coding theory, maybe in 90s, I think 93 or so. Okay. People came up with this turbo codes. These are near channel capacity codes which are also practical. These use a very simple technique. Okay. So how do you increase the length of a code? Okay. So if you start, you know that for small length codes, they are very easy to handle. Encoding is easy, decoding is easy and all that. But as you increase the length of the code, it becomes harder. How do you increase the length of the code keeping this under control is a technique called concatenation, which means you encode and you like concatenate it with another encoder. Okay, so the effective length that you get is encoder 1 output, which is n1 times n2. That is the total length of the code. Okay. So there are different ways to do this concatenation, right? So one is called serial concatenation, which was there before the turbo codes were invented. Okay. So you have some set of message symbols. In the serial concatenated codes, what happens is that you have a set of message symbols and there is a code. Okay. Earlier we saw that our code was a code over F2. Our generator matrix was taking symbols 0 and 1. Okay. But there are some objects called finite fields. Have anybody heard of them? Finite fields? Okay, not many, but they are, let's say, some generalizations of F2. So the thing is, this is instead of F2, there is a field called F2 power something. Okay. That's a finite field. So that is definitely a larger alphabet or a larger source space, sample space to pick from than this F2. Okay. So this code is over a larger alphabet. This is called an outer code. So you take the output of this and map all these symbols back to bits and code it using an inner code. Okay. So this is why it's called a concatenated code. There is an outer code and there is an inner code and you are getting output bits. So this is a serial concatenation because this is coming after this. So this were before, okay, but the major breakthrough in terms of turbo codes was what was the idea of parallel concatenation. So you don't put encoder 1 after encoder 2, okay, but what you do is that you keep pumping in your message bits through encoder 1, interleave these message bits, interleave in the sense just randomly permute. Take your message bits and just randomly permute. That's called interleaving. So you interleave them and feed it to encoder 2. So whatever you are getting in the end, message bits, parity bits, that is your code word. So this code was, as you can see, the complexity is either that of encoder 1 or encoder 2. Okay. Just maybe the max of those two. But if you would have used whatever length you are getting directly with one single code, then the complexity would have been much higher. So in that sense, you stored on encoding complexity, and even decoder will have a similar structure, and in that sense you will be saving on the decoding complexity also. So this is one class of codes which are used, have very wide applications. You take your 3G, 4G, any standard turbo codes are there. You take your digital broadcast, TV broadcast, satellite, turbo codes are there. Mars, you're going to send your spacecrafts, turbo codes are there. So they are so powerful. But one major drawback of, not in terms of drawback, this is a code. The thing is, even to this date, theoretically this is very less understood code. Though it has been employed so much, yeah, still theoretically there are many more challenges as to why these codes behave so well. It's not completely nailed down. It's not. So there is another set of codes. Okay. So previously we used the technique of concatenation in order to increase the length of the code, right? So here there is another technique which is used, which is simple. So these are called LDPC codes, low density parity check codes. So why are they called low density parity check codes? Your parity check matrix is sparse. You understand what is sparse? So parity check matrix totally has n minus k cross n entries, possibly all variables, okay, but the number of non-zero entries in that will be very, very less, okay. So that is what is called sparse. So this parity check codes has low weight code words and it is very sparse. So with this idea, okay, this is the main idea behind LDPC codes. Okay. Then the main advantage of this LDPC codes is that it can be decoded very easily. There is a very nice algorithm which is called message passing or belief propagation. We will get to that. But it is used in many other contexts also. It's not one algorithm which is used in this context. It's used in many other contexts. But in this context, I'll just explain. So in order to get to that algorithm, we have to represent this parity check matrix H like this. Okay. So we are denoting the 7 columns with the 7 nodes. These are called variable nodes. Okay, and whatever equation this is representing, we will represent by 3 check nodes. So, and we make a connection between, so you understand what is C1? C1 is connected 1, 2, 3, 4, and those things are connected here. Okay, and similarly C2, 2, 3, 4, and 6 are connected. So this is called a Tanner graph, and this is basically a bipartite graph representation of H. So this can be done for any code. So the important point in LDPC codes is that the variable nodes and the check nodes have very less degree compared to the total number of edges in the graph. Okay, so these have very less degree. So now what is the belief propagation algorithm which is used? Okay. So this is the same picture. So this belief propagation, so any other algorithm other than the maximum likelihood that I talked about initially is going to be a suboptimal one, because ML is the optimal decoding algorithm, but ML is very, very hard to implement. Okay, if you want to really implement ML, it's going to take a lot of CPU cycles. So a low complexity version which actually converges to this ML performance is what is this message passing algorithm. So what are the messages? So basically the simple idea to take away here is that there will be some message exchanges between this LHS, I mean left hand set of nodes and the right hand set of nodes. There will be some messages getting exchanged, and there will be some iterations. Okay. And what are the messages that will be exchanged? They are probabilities. Okay. So probability that a certain symbol is 0 or probability that a certain symbol is 1. So this is a belief or a probability, and these probabilities will be exchanged between the set of variable nodes and the set of check nodes. So this is how the message will be. It's just a depiction of a message. Suppose if the variable node V4 wants to send some message to, the check node C2 wants to send some message to V4. Okay, so it will basically send, see, all your code word symbols are only on this. The check nodes have nothing. Okay, they are just your parities. Okay, so when you receive a vector of 7 length, it has to be mapped to these variable nodes, right? So V1 to V7 already have some output of the channel with them. Okay, but they are talking to check nodes to agree upon something, right? So, and that is what this message passing actually does. So they'll keep talking to these check nodes and finally reach a stage where they agree in some iterations and say, okay, I have converged and this is my output. Okay. And there is a simple rule to do that. Perhaps I will not go into the details of that as of now. So LDPC code applications, again this LDPC code is a major competitor for turbo codes, but still there is a catch that LDPC codes still have high encoding complexity. Okay, and people are coming up, trying to come up with ways in which the encoding complexity can be made smaller and smaller. So they are used in DVB. So what happens is that in these standards, everybody has their contender code, okay? And they have to show their performance curves and all that, and to push through the standard, it's like so many codes will be competing. So LDPC code, which might have been competing here, and in one instance it won against turbo codes. Ethernet, WiMAX, all kinds of applications. I think I am running out of time, so I'll just perhaps skip the storage slides. If you are okay, but I'll tell you something very recent. What is happening? So recently there have been a set of codes called locally repairable codes, okay, which are advancements over what are called Reed-Solomon codes, which are very famous in coding theory. Okay, they are defined over large finite fields and all that, but there are very good codes to use in CDs. Okay, so the Reed-Solomon codes are used in CDs, barcode scanning, and all those things. Okay, so but as data centers are picking up, right, they also try to use these Reed-Solomon codes. But data centers typically store petabytes of data and they store it in a distributed fashion. So in that setting, nodes keep failing. That means some computer is there and it failed. Okay, and you have to repair that with another thing. But it had petabyte of data, so you have to repair and get your petabyte of data and put it back, right? So in that setting, Reed-Solomon codes are found to be bad. And Windows, Microsoft team had come up with a nice code. You can perhaps look it up, where they split the message bits into some what are called local codes, okay? And then, so basically they have a certain code structure. They have 2 local codes, and these are what are called global parities. So in Reed-Solomon code, what would have happened is, if 12 message symbols are encoded, in order to repair even one node, you need to access all 12 of them. That is a property of Reed-Solomon codes. So these people have said, okay, I'll split these 12 into 6 and 6 and put some what are called local parities. And with this, Microsoft claims that they have shipped their Windows 8.1. They have shipped their, the all latest versions, whatever you can think of. So these are called locally repairable codes, or they call it something else, okay? But this is 2012 to 2013 work. I just wanted to draw your attention to that. So this is used in data centers. That's all. Any questions?
Any questions? Thanks, Lalitha, for this